Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a concept of specific speed and we'll derive its equation and we'll find out the significance of specific speed of turbine. So this specific speed we are going to derive of turbine. So first of all, we'll see what is specific speed. So actually the specific speed of a turbine is defined can be defined as which is in identical in shape and size or dimensions or blade angles or gate openings, which with the actual turbine, but sized in such a way that it will develop only one unit power. We can say one unit power will be developed with a 1 unit head. We can say only one head, suppose like unit power will be developed 1 unit head. That means we need to create a turbine and we need to test in such a way in under 1 unit head, and that should develop a 1 unit power. So this is for testing purpose, or you can say why it is required for a turbine. So this specific speed will be defined, it will be identified to identify which category of turbine it is and what purpose we can use this. So speed, we know that it will be defined in RPM. Okay, so based on the speed we can select the turbine, what kind of work is there and which kind of turbine will be selected. So that from the specific speed it can be identified. So this is actually we can like create a model and we can test the turbine under a unit head, how much whether unit power is developed or not. Okay, so the 1 unit power will be developed under a working head of 1 unit head. Okay, and this specific speed is defined, or it is denoted by NS. Okay, so this, as I told you, this will be used for comparing different types of turbine. Okay, under different specific speed, because each turbine is having different speeds are there. So to identify to compare different turbines, the specific speed is must required. And the unit power, actually what I told you, that the unit power will be taken. This will be two types are there. For one is for SI units, another one is for MKS units. So 1 unit power that will be taken for like 1 HP. Okay, 1 horsepower, and and a unit head of 1 meter, and unit head that will be 1 meter. So this will be considered 1 unit head, that is as 1 meter, unit head as 1 meter. So this will be considered for SI units. Okay, similarly for the MKS unit, if you consider, so that unit power, that 1 unit power will be taken as 1 kilowatt. Okay, and here the unit head will be same like 1 meter only considered here also. Okay, so no, this is 1 HP given, so this need to be considered for MKS, not SI. This is MKS unit and this is our SI unit. Okay, now we'll derive this specific speed from the efficiency. So we know that overall efficiency equal to, we have seen, that is we have derived in our efficiency video, that is shaft power by water power. So shaft power, we know that can be written in the power P, and the water power is calculated with the formula of like rho g QH by 1000. Okay, and here we can write the power P equal to, we can write in such a way that we will take this term to that side and remaining term will be here. So P equal to, we can write this is efficiency, overall efficiency, into here, okay, rho into G into H, rho into G into H into Q divided by 1000. And here what are the terms I have written here? I hope you know these terms. Like Q, we know that this is the discharge through the turbine. So Q is nothing but discharge through the turbine, and here P already can be, I have written already, this is shaft power, the power developed, and H H is nothing but head under the turbine is running, you can say, or the turbine is working. Under the turbine is working. So this is discharge unit is meter cube per second, and here head we can write this is meter, and rho is the density. So these things, basic things, we know this one. So this is kg per meter cube, the unit is this, and yeah, G is the gravity, head is their overall efficiency. Okay, now from here if you see this equation, this is our constant term. This three parts, if you see these parts, all total all are constant term. Overall efficiency is constant, fixed. G rho is density fixed, G is fixed. So remaining terms are there, where I can write the P is directly proportional to our Q, and also Q into H. Like H is there, head. As for the head variations are there, we can vary the power will be also varied here. So P is directly proportional to Q into H, we can write, and this one we just mark as equation number 1. So again, few terminology will be there when you write this Q equal to area into velocity, we know, and area if you calculate we require the diameter. So let's consider some other terminologies like D, which is nothing but diameter of actual turbine, diameter of actual turbine, and that can be marked as like meter unit. And similarly, we need to consider some velocities like U. If we consider, that is our tangential velocity, we know that this is our tangential velocity. The same terminology we used to consider sometimes peripheral velocity also. So this is tangential velocity of turbine. And next is V. V is what? V is, we know, the impact of jets or the jet of velocity, or we used to call this is absolute velocity. This is also called absolute velocity. So here also we need to, if we want to write the unit, we can write this is meter per second. This is also meter per second. Now N equal to, this is actually speed of the actual turbine. Speed of actual turbine. Speed of actual turbine, and which can be written in like RPM. Okay, and now this N S equal to, this is specific speed. This is specifically we used to design or we used to calculate this, that is specific speed actual of turbine. So these are the some terminology which are used here, and we know that absolute velocity and tangential velocity and the head, which all are related. So this tangential velocity also depend upon the absolute velocity, that we know. So absolute velocity or tangential velocity can be calculated from the actual velocity or absolute velocity also. So we can write that U is directly proportional to V, and again I can write V is directly proportional to root over of H. You can ask how it is possible. We know one equation, that is velocity, absolute velocity V1, we have derived previously, that is from like root over of 2 GH. Here we used to give the CV value, some coefficient of velocity, or else we can, because this is the constant term, we know this equation. So from here 2 constant, G constant, CV also constant. So we can write V1 is directly proportional to root over of H. Now from this equation, if you see, we can write like U is directly proportional to H. U is directly proportional to H, and this one will give an equation. Okay, this equation we can give equation number 2. Equation number 2 here. Okay, and also we know that one more terminology, the tangential velocity also can be written this equal to, we know that pi d n by 60. So here d equal to diameter, n equal to speed. So if you see the constant term, pi is constant, okay, and 60 is constant. So remaining two terms are what? One is d, another one is n. So from here we can write U is directly proportional to D into N. And here I can write one more equation, equation number 3. Now, if you see these two equation 2 and 3, we can write easily what? U is there, U is there. But like U is here, U is here. So here we can write root over of H is directly proportional to our dn. This also can be written. And from here again I can write, this is like, we can write, not implies, d is directly proportional to root over of H by n. This one I give equation number 4. This is another one equation, I can mark it here. Now the discharge we need to calculate, diameter we have calculated. Next we will try for the discharge. Okay. Now head we got here, head term, one terminology is there. Now the next part for us is, this is discharge. So discharge through the turbine. Discharge through the turbine. We can write, we know the formula as I told you starting, we know that Q equal to A into V. So, and here area we can write what? Area, we know that, what is the unit of this? Unit is meter square. Okay, here area I have not mentioned. One more terminology, we can write, this is area. Okay, area is meter square. So area meter square in the sense, we can write either length into height, or we can write this is breadth into depth, or we can write any one terminology, breadth into height, otherwise you will take it here. Okay, or we can write length into breadth. Some terminology we can consider here for the area. So in the area term I can write one here, like A equal to, A is directly proportional to, suppose if we consider H and B, or depth and breadth, so I can write here on behalf of H, I can take the D also, no, there is no issue. So area we can directly proportional to B into, suppose depth is there, because we have considered the width and depth we have considered there. So B is the width here. So here we can write, this is B is the width here. Okay, and if I consider this one, so I can write here, yeah, this also can be considered like diameter also will be there, and this is breadth also. Anyway, dimension required, meter into meter, so that will be area in, that is meter square. So also here we can write area is directly proportional to d square, because I can write, I know that B is also equal to D, or B is directly proportional to, also I can write D. So area I can write is directly proportional to d square. This is area part. What about the velocity here? So velocity already we got previously. So we'll write this one. Velocity what we got here? Velocity directly proportional to H from this equation. So what I'll just put the value in this equation. Q is directly proportional to A. Area plate what I will write, that is d square, into what is the, in place of V what I'll write, already I got here H, that is like root over of H, what I got, I'll just put this value. Next, so what I can write here next, like Q is directly proportional to, in place of d square, any term is there, yeah, this term is there for d value. So let's put the value here, like root over of H divided by N whole square. D square is there, into, we can write root over of H. So from here what we will get here, like Q is directly proportional to root over of H square. So we can get only H, and denominator N is there, so that will be N square, into, we'll get root over of H, this equation. And again I can write Q is directly proportional to H, and this is root over H to the power 1 by 2. If I'll just multiply, that means the power will be added. So 1 plus 1 by 2, that will be 3 by 2. So we can write H to the power 3 by 2 divided by, this is N square. This is our equation number, suppose 5. This is our Q. Now what we'll do, initially if you have seen one equation like P is directly proportional to Q into H, we got the value of Q, we got the, our H is there, just we'll try to put the value here. Next, we can write, substitute the value in the first equation, that is nothing but P is directly proportional to, like H into Q. So what is the value of Q here? Q is nothing but H by, okay, H to the power 3 by 2, and this is N square into, we have H value, okay, in the starting equation, first equation. Now what I can write here, if we solve this one, I can write P is directly proportional to, again, 3 by 2 plus 1. So that will be like 5 by 2. So this is H to the power 5 by 2 N to the power N square. Okay. Now what I can write here, P equal to, I can write this is K H to the power 5 by 2 divided by N square. And here what is the meaning of this K? So K is nothing but this is a constant of proportionality. To avoid this direct proportionality, we just included one constant of proportionality, that is K. Constant of proportionality. Okay. Now to find out this K value, if suppose P is 1 power and which is working under one head, that is also 1. Okay. So the speed n, what will get here, n, specific speed n, and specific speed also, let's consider P1 H1, and the speed n is ns. Okay. The specific speed needs to work under one pressure, one unit power and 1 unit head, we have stored, I've told in the starting. So just you put this value in this equation, then what will get, like P place, in place of P, what I told you, 1. Then K is there as usual, and here H, what is the value of H? 1. And this is ns square. So what I'll get here, ns square equal to K. So now again I can write, just put the value of K in this equation. So finally I'll get here like P equal to ns square H to the power 5 by 2 divided by this is n square, sorry, this is n square only. And also I need to find out the specific speed, so I'll keep the ns square here, and this can be written n square P divided by H to the power 5 by 2. Or if I want to write only ns, that can be written in terms of like n square P divided by H to the power P. Again, if I want to write again in details, like I can write in this way, H to the power 5 by 4. This is ns. This is our specific speed, and this can be given equation number 6. Up to 5 you have given equation, now you can give equation number 6. So this is the specific speed of a turbine we can calculate. So as I told you, the significance of the specific speed will be like different categories will be there. I'll tell you that just for SI unit symbol, how we can identify the specific speed. So the specific speed for which type of turbine can be identified. So this is type of turbine, suppose. Okay. I'll just tell you the values of specific speed. So in SI, because both are there in SI unit and MKS unit, both are different. So for SI unit, if the value we got 8.5 to suppose 30, so this will be given like symbol of Pelton turbine with single jet. Similarly, if we got the value of like 30 to 51, okay, so this also like Pelton turbine with more jets, will get more jets. Similarly, the value which is more than 51 to 225 or 255, suppose. So this will be give the indication of that this is a type of Francis turbine. This is the turbine of Francis turbine. Again, now if the value will get 255 to like 860, so this will be give a hint of like Kaplan turbine, or we can say this is propeller turbine is there, one more is there. So this is the value of specific speed, okay, to identify different types of turbines. This is this one I just told you about the SI units. Similarly, in MKS also similar kind of, just values slightly different are there for that. So this is all about the specific speed of a turbine, which is very, very essential, again, I'm telling you, to identify or to select the type of turbine, and how, and the performance of turbine also can be predicted from the specific speed. So these are the two things we need to require in our mind to select the different types of turbine, and how to identify the performance of the turbine. This specific speed is plays an important role in that. I hope you understand this derivation of the specific speed and its significance. Still, if you are having any kind of query and doubt regarding this, you can give a comment in the comment box. Thank you all.